Hello everyone, myself Harish Kannati. I am the PMR fellow at IIT Roorkee Department of Hydro and Renewable Energy. Today we are going to discuss assignment 9 problems. This basically discuss about the AC networks. The first question is calculate the voltage at node 2 for the circuit given below. Means we have to calculate the sorry yeah we have to calculate the voltage at this particular node. Let us suppose we can consider this as a V2 and consider the node voltage is V1. Okay, so one can apply the KCL at this particular node V1. Let us consider this the direction of current I1, this direction of current I2, this is direction of current I3, this is I4. At node V1, what is the KCL? This sum of all currents, right? It is I1 plus I2 plus I3 plus I4 equal to 0. What is the I1 here? I1 we can write it is a current through this J4 ohm inductor, which can write written as V1 potential difference across the inductor V1 minus V2 by the impedance of that particular inductor, that is J4 ohm, plus how can we write I2? I2 is simply here the voltage is V1, so the potential difference across this particular capacitor is V1. So we can write V1 by the impedance of the particular capacitor is minus J2 ohm. Similarly, how can we write I3? I3 is same as this, same potential is applied across this 10 ohm resistor also. So V1 by 10 ohm. And what about this I3? Sorry, this is I4. Yeah, we can. I3 is the I3 is direction of the, this one is I3, right? I3 is same as the current source, that is 20 at an angle of 30 degrees, plus I4 is the current through the 10 ohm resistor, which is V1 by 10 ohm equal to 0. We can write V1 terms together, which can be 1 by J4 ohm plus 1 by minus J2 ohm plus 1 by 10 plus V2 terms together, V2 is minus 1 by J4 ohm equal to minus 20 at an angle 30, right? So what is the equivalent of this particular term? It is 1 by J4. You can use your scientific calculators and find out that particular value, that is 1 by J4 ohm plus 1 by minus 2J plus 1 by 10, which is of B1 into 0.1, sorry, 0.1 plus J 0.25, right? And plus P2. What is the value of minus 1 by J4? Minus 1 by J4 equal to 0.25 J equal to minus 20 at an angle of 30 degrees. This is the KCL equation at node 1. We can consider this as a equation 1. Similarly, we can apply KCL at this particular node 2. Okay, now you can consider the directions of current Let us suppose this is as a IA, and this direction of current we can consider IB, and this is IC, and this is ID. Okay, what is the KCL equation at node 2? That is V2 equal to sum of the all currents, right? It is IA plus IB plus IC plus ID equal to 0, right? How can we write this IA? IA is the current flowing through 4 ohm, that this direction of the current, right? How can we write this IA current? It is potential difference across this J4 ohm. The potential difference is, we have to consider this is as a reference potential, it is V2, this is V1. So the potential difference is V2 minus V1 by J4 ohm, right? That I V2 minus V1 by J4 ohm. Similarly, how can we write IB? IB is the current just opposite direction to the current source, right? So we can write IB equal to, just with negative sign, 30 degrees. Why? Because the IB is same as the current source current, but the direction is opposite, so we put negative sign here. Similarly, IC IC is IC is the current flowing through this 2 ohm inductor. It means the potential at this across this 2 ohm inductor is same as this V2. Why? Because the J2 ohm inductor is connected in between the node 2 and the ground. So the current through the 2 ohm inductor, we can write the potential across the 2 ohm inductor, the J2 ohm inductor, by J2 ohm. What about ID? ID is the current through this minus J5 ohm capacitor. It means the voltage across this minus J5 ohm is same as the V2. Why? Because it is connected in between the node 2 and the reference node, that is ground. So how can we write this ID? It is simply V2 by minus J5 ohm equal to 0. We can separate V2 terms and V1 terms separately. We can write V1 equal to minus 1 by J4 ohm plus V2 equal to 1 by J4 ohm plus 1 by J2 ohm plus 1 by minus J5 ohm, right? Equal to this term, we can, this particular term we can send it to that side. It will be 20 at an angle of 30 degrees. What is the equivalent of minus 1 by J4 ohm? Just we calculated here, it is minus 1 by J4 ohm equivalent is 0.25 J. I am just writing the same thing, 0.25 J plus V2 into, what is the value of this particular term? We can use scientific calculator, 1 by 4J plus 1 by 2J plus 1 by, I think it's minus 5J, right? Yeah. 1 by minus 5J, which is equal to minus 0.55 J equal to 20 at an angle of 30 degrees. This is the KCL equation at node 2. We can consider the equation 2. From equation 1 and equation 2, from 1 and 2, what is the equation 1? Just From equation 1 and equation 2, we can find out V1 and V2, right? So we can find V1 and V2 from 1 and 2. It will be, you can use equation solver. The P1 constant of the T, this one is 0.25J. Yeah, shift that, sorry, yeah, 0.25J plus minus 0.55J minus 0.55J, yeah, plus equal to 20 at an angle of 30 degrees. That is equation 1, sorry, equation 2. Coming to that equation 1, it is 0.1 plus 0.25J, then this constant is 0.25J, and this one is minus 20, shift at an angle of 30. Yeah. Now what is the value of V1? V1 equal to minus 20.58 plus J 20.319 volts. And what about V2? V2 is minus 27.539 plus J 40.72 volts. We can representing the, sorry, complex, yeah, minus 20.58 plus 20.319 J, which is equals to 28.92 at an angle of 135.36 degrees. What about V2? V2 is minus 27.539 plus 40.72, shift polar form, it is 49.158 at an angle of 124.07 volts. So the voltage at node 2 is same as V2. First we consider this node V1, we applied the KCL at this particular node, and second we consider this node 2 and we applied the KCL at this particular node, and by solving those two equations we will get this V1 and V2 values. Yeah. Second one, calculate the voltage V0 for the circuit given below. What is the value of V0? V0 means the voltage at this particular node. Okay. Same as we can apply KCL at this particular node. So consider this current as I1 and this current I2 and this current I3. How can we write KCL equation at this particular node? That is I1 equal to I2 plus I3. I1 is the current which is same as this current source current. Why? Because these two are in series. So I1 is 4 at an angle of minus 30 degrees equal to, what about I2? How can we write I2? I2 is the current flowing through this particular 2 ohm resistor. So here the voltage, let us suppose it's reference. Here the voltage with respect to reference is V0. So how can we write this I2? I2 is the voltage across the 2 ohm resistor, that is V0, by resistance of that particular resistor which is 2, right? How can we write I3? The the potential difference across this particular J4, right? What is the potential at this particular point? Here it is 0 volts. Why? Because we consider this particular node as a reference node. What about this voltage at this particular node? It is minus 3 V0, right? So the potential difference across this particular J4 ohm is voltage at this point minus voltage at this particular point. At this point, the voltage is V0. At this point, the voltage is minus 3 V0, right? So the potential difference we can write V0 minus of minus 3 V0 by J4 ohm, right? That is 4 at an angle of minus 30 degrees equal to V0 by 2 plus V0 minus of minus, we can write plus 3 V0 by J4 ohm. So 4 at an angle of minus 30 degrees equal to V0, we can take it out, is 1 by 2 plus 4. Why? Because 1 V0 plus 3 V0, it is 4 V0. We can take the common as the V0 by J4 ohm, which is this 4 and 4 will be cancelled, then V0 1 by 2 we can write it is 0 0.5, 1 by z is minus j. So V0 equal to 4 at an angle of minus 30 degrees by 0 0.5 minus j is equal to 4 at an angle of minus 30 divided by 0 0.5 minus j, which equal to 3.57 at an angle of 33.43 volts. Okay, we consider this particular node and we applied the KCL at this node. We consider this node as a reference node because it is a common node. So the voltage across at this particular point with respect to our reference node is minus 3 V0. So the potential difference across this J4 ohm is V0 minus of minus 3 V0. It is potential difference is 4 V0. So we can write this I3 as V0 minus of minus 3 V0 by J4 ohm. Then I2 is simply it is a voltage across this particular resistor 2 ohm resistor is V0. So the current through this particular 2 ohm resistor is V0 by 2 ohm. And here the current is here the I1 is series with the current source. So I1 we written directly. This is a 4 at an angle of minus 30 degrees. By simplifying that particular equation, we will get this V0 equal to 3.57 at an angle of 33.43 volts. Okay. Coming to the third one, calculate the current Ix for the circuit given below. Okay. Here you can go through either KVL equation. How many loops here? Here 3 loops are there. It means you will get 3 equations and you have to solve these 3 equations. You will get the 3 currents through the loops. And how many nodes here? Here it is like a reference node, and here one node, and here one node. No, number of nodes are 2 nodes plus one reference node. If you apply KVL, you will get 3 number of equations. If you apply KCL, you will get 2 number of equations. It means to solve this particular problem, it is by applying the KCL, you will get 2 equations. It is easier. So we are going to apply the KCL equations, that is nodal equations, at these 2 nodes. Suppose this is V1 and V2 at these 2 nodes. and we will find out this node voltages, then we will find out this particular current Ix. Okay, same as previous nodal analysis means we have to apply KCL equation at that particular node. Let us consider this direction of current I1, this is I2, this is I3. How can we write this KCL equation at this particular node V1? It is simply all current directions are we consider leaving direction. So it is sum of these currents. It is I1 plus I2 plus I3. How can we write I1? I1 is, we can write I1, which is potential across this impedance by this particular impedance, right? What is the potential across this particular impedance? Which is V1 minus the potential at this point, it is 60 at an angle of 0. What is the impedance? The 2 ohm resistor and J4 ohm inductor are connected in parallel, sorry, series. So it is 2 plus J4 ohm. What about I2? I2 is simply the current through the 6 ohm resistor. We can directly write V1 by 2. What about I3? I3 is, it is V1 minus V2 by minus J2. So how can we write this V1 model equation at V1? V1 is I1 plus I2 plus I3, right? I1 is V1 minus 60 at an angle of 0 by 2 plus J4 ohm, plus I2 is V1 by 2 plus I3 is V1 minus V2 by minus J2 equal to 0. You can simplify this thing. You can write V1 terms together. V1 equal to, yeah, sorry, thank you for reminding. Thank you for reminding. It is because it is the current through this 6 ohm resistor. It is the potential across the 6 ohm resistor, that is V1 by 6 ohm. Sorry, thank you for correcting me. This is 2 plus J4 ohm plus V1 is 1 by 6 plus 1 by minus J2 plus we can write V2 terms here, which is of minus 1 by minus J2. We can bring this 60 at an angle 0 to this side. It is 60 at an angle 0 by the denominator. It is 2 plus J4. It is negative sign, it will becomes positive. So we can find out this equivalent, which is of 1 by 2 plus 4J plus 1 by 6 plus 1 by minus 2J, which equal to 0.267 plus 0.3 J plus this minus and minus will be cancelled, and V2 into what about 1 by 2 means 1 by 2 J means it is minus 0.5 J equal to 60 at an angle 0 by 2 plus 4J, which is equal to 13.41, yeah, 42 minus 63.443. This is the equation at node 1. We will consider this as a equation 1. Similarly, the KCL equation at this node 2, that is the KCL equation at V2, we can consider the directions of the current. Let us suppose this is IA and this is IB, this is IC. So what is the KCL equation at this particular node 2? At node 2, that is at node V2, the KCL equation is IA plus IB plus IC equal to 0. Why? Because we consider all the current directions are leaving direction, so the algebraic sum is 0. What is the IA? IA is the current in this direction. It is just opposite to the this current source direction. So we can write IA is same as this magnitude, but the direction is opposite. So we can represent IA equal to the magnitude remains in 5 at an angle of 90 degrees, but it will be negative side. Why? Because the direction is opposite direction. Similarly, IB is, what is the IB? IB is the current flowing through this 4 ohm minus J3 ohm impedance. What is the voltage across this 4 ohm and minus J? What is the voltage across this 4 ohm and minus J3 ohm? It is V2, right? Why? Because it is connected in between the node 2 and the reference node. So the voltage across this impedance is V2. So we can write IB equal to the voltage across this particular impedance V2 by total impedance, right? The total impedance is these two 4 ohm and minus J3 ohm are connected in series. So it is simply 4 plus, so 4 minus J3 ohm, right? Why? Because these two are connected in series, the total impedance is 4 minus J3 ohm. What about IC? IC equal to the current flowing from V2 to V1. It means the current flowing from V2 to V1. This is our IC. What about the potential difference across this minus J2 ohm capacitor? It is V2 minus V1, right? Why? Because we are assuming the direction of the current which is flowing from V2 to V1. So our greater potential is V2 and lesser potential is V1. So the potential across this minus J2 ohm is V2 minus V1. Whatever the impedance of minus J2 ohm capacitor, it is minus J2 ohm. So we can write IC equal to the potential difference across this minus J2 ohm is V2 minus V1 by minus J2 ohm, right? It is V2 minus V2 minus V1 by impedance of this, that is minus J2 ohm. So we can substitute this all three in this KCL equation. So which is minus 5 at an angle of 90 degrees plus IB, which is V2 by 4 minus J3 plus IC, which is V2 minus V1 by minus J2 equal to 0. Okay, we can separate V1 and V2 terms. So V1 equal to minus 1 by minus J2. Here this term I do this term, that is V1 is minus V1 by minus J2, which is minus 1 by minus J2. So this minus and minus will be cancelled. It is 1 by J2. What about V2 terms? V2 terms are 1 by 4 minus J3, this particular term. And what about this term? It is 1 by minus J2. we can send this term to that side. It will becomes 5 tan angle of 90 degrees. This minus will be cancelled. So we can find out this equivalent values, which is 1 by j2 means it is minus 0.5 j, and v2 sorry plus v2 into 1 by 4 minus 3, 1 by 4 minus 3 j, yeah, plus 1 by minus 2j, which is equal to 0.16 plus 0.62 j equal to 5 at an angle of 90 degrees. This is equation 2. By solving equation 1 and equation 2, about the equation 1, we will snip this equation 1. So yeah, we will solve this equation 1 and equation 2. We will get the values of v1 and v2. We will use that equation solver, which is the constant of this particular one is minus 0.5j, minus 0.5j, and v2 constant is, it is 0.16 plus 0.62j, and constant is 5 at an angle of 90 degrees. And similarly here the constant is 0.267 plus 0.3 yeah, and this constant is minus 0.5j, and it is 13.42 13.42 at an angle of minus 63.43, okay, which is equal to 17.80 minus j 18.74 volts. And coming to the v2, it is 24.678 minus j 8.746 volts. We can write this, it is 17.80 minus 18.74 j in polar form. You can write it is 25.846 at an angle of minus 46.47 volts. Similarly, this V2 value is 24.678 minus 8.746 J in polar form, which is 26.181 at an angle of minus 19.51. This is V1 and V2. What is our question? We want Ix. Ix is the current flowing through this particular arm, right? The potential across this particular impedance is V2, and the current through this particular arm is, we can write simply from Ohm's law, it is V2 by impedance of that particular arm, right? That is simply 4 minus J3 ohm. So Ix is, we can write Ix equal to potential across that particular arm, it is V2 by impedance of that particular arm, it is 4 minus J3, is 4 minus J3, which is equal to 26.181 at an angle of minus 19.51 by 4 minus J3, which is equal to 26.181, shift at an angle of minus 19.51 divided by 4 minus 3Z in polar form, yeah, which is equal to 5.236 at an angle of 17.359. Here we just calculated the voltages of this particular node V1 and V2. Why? Because we want to find out the current through this node. So first we calculated this node voltages, and from this node voltages we found out this Ix. Why? Because the same node voltage is applied across this particular branch. So the current through this particular branch is the voltage across this branch by impedance of that particular branch, simply from Ohm's law. So first we found out this V2 and V2 by the impedance of this particular node, that is 4 minus J3, which will gives the Ix. The next question, the primary of the ideal transformer. Ideal transformer means efficiency equal to 100%, and with the turns ratio of 5, the transformer turns ratio is 5. What is the meaning of the transformer turns ratio? Transformer turns ratio is the ratio of primary turns to sorry is to by N2 by N1. N2 is the number of turns on the secondary side, and N1 is number of turns on the primary side. Usually transformer turns ratio means N2 by N1. N equal to 5 means, okay, which is equal to V2 by V1 equal to I1 by I2, which is the transformer turns ratio meaning. And connected a voltage source with a Thevenin's parameters VTH equal to 10 cos 2000 T volts, means VTH equal to 10 cos 2000 T. Is there any angle? No. Volts is the applied VTH. And what about the RTH? RTH equal to 100 ohm. Determine the average power delivered to the 200 ohm resistor, that is load connected across the secondary windings. We can redraw the circuit, which is here there is a one voltage source which is of magnitude VTH. VTH and RTH are connected in series. So this is the source. Okay, the source is connected to a ideal transformer. The turns ratio of the ideal transformer is 1:5. Okay, and one resistor load is connected across the secondary. This is RL. So here RL equal to 200 ohm and RTH is 100 ohm. Okay, now we need to find out what is the power, this average power delivered to this particular 200 ohm resistor. Okay, we can refer this 200 ohm resistor equivalent to this side by considering power balance equation. It means we are consider this PRL, let us suppose that is load power. Here transformer is ideal means whatever the power delivered to this particular RL is the power delivered to the primary terminals, right? Why? Because this is ideal transformer, so the losses in this particular transformer is zero. So whatever the load power is same as P primary. Okay. What is the load power? Load power equal to, we can write, let us suppose this current as I2, the secondary current. We can write I2 square into R2. Why? Because the current through this resistor, sorry, RL, the current through this resistor into the resistance. Why? Because simply the power dissipated across the average power is I2 square into R2. The same power is delivered to the primary, right? So the primary P primary equal to I2 square into R R2, right? What is the current here? Here the current is I1. What is the resistance seen from this particular primary terminals? It means we are assume this is as a RTH. It means we are assumed some resistance R. Okay, let's suppose the prime R2 dash. Why? Because it is the equivalent resistance of this load resistance. So here the current flowing through this particular one is I1. So what about the primary? It is I1 square into R2 dash. Why? Because we are equating the power balance equation. What about the what the amount of power dissipated at the secondary side? The same amount of power dissipated even though if it is referred to the primary side. What is the equivalent resistance? We can write R2 dash equal to I2 square. We can simply refer this I1 square by I1 square into R2. So the R2 dash equal to I2 by I1 square into R2. What is the value of I2 by I1? I2 by I1 is 1 by 5, right? It is 1 by 5 whole square into R2. R2 value is 200 ohm. What is the value of 1 by 5 square? It is 1 by 25 into 200 ohm. It is 8 ohm. It means the circuit, which is VTH, RTH, and 8 ohm, 100 ohm, and VTH. This circuit is same equivalent of this particular circuit. It means the what about the amount of power dissipated by this 200 ohm, the same amount of power dissipated by this 8 ohm system. So we can find this current through this thing and power. Whatever the current, it means it is simply connected. It is VTH by this 100 ohm plus 8 ohm, right? 100 ohm plus 8 ohm. It is VTH is 10 cos 2000 T. Yeah. 10 cos 2000 T by 1 not, sorry, 1 8 amps, which is equal to I1 equal to, what is the value? 10 by 108. It is 92.59 cos 2000 T milliamps. So what about the power? Power equal to P load. This is P load equal to the current, the RMS current through this 8 ohm resistor, that is IRMS square into R, right? What about the RMS value of this particular thing? RMS value equal to maximum by root 2, is equal to 92.59 milli by root 2, which is equal to 65.47. The I1 RMS equal to 65.47 milliamps. We know the value of the RMS current and we know the RL equivalent resistance, that is 8 ohm. So we can find out the power equal to IRMS square into RL. That is 65.47 to 10 power minus 3 RMS square into load resistance, that is 8 ohm, which is equal to square into 8 ohm, which is of 65.47 into 10 power minus 3 whole square into 8, and this 34.29 milliwatts. It is the power dissipated by this load is, the average power is 34.29 millivolts. First, he gave he given that there is a Thevenin's voltage source in series with the Thevenin's resistance is connected to the primary terminals of the transformer. Just we connected VTH and RTH to the ideal transformer, and a load of 200 ohm is connected to the secondary side of the transformer. So we have the transformation ratio. We referred this load resistance equivalent at primary side. Means simply we connected one resistor here which is equivalent to the resistance seen from these terminals, that is 8 ohm resistor. It means this simply that the resistance seen from this terminals is 8 ohm resistor. The power dissipation of across this 8 ohm resistor is same as the power dissipated at the load resistance. Why? Because the power drop, that means the efficiency of this particular transformer is 100%. So the what about the power is 34.29 milliwatts is completely delivered to the load resistance. Why? Because this is a ideal transformer.